the straight line portion, if I had made it thinner, it would have been, but given that I don't trust my drawing skills very much, I'm going to sample thick.
You can still make it thinner, just touch the side.
Yeah, I don't trust my drawing, that's good. That's perfect. That would be full credit if you do that. Okay? So that's a good slope line. So I hope I see from everyone a good slope line. All right. So, what is t-coordinate? It's where this line intersects the original steady state, which is at 150. This is spacing 50, 60, so each line here is 2. So 52 is here. It's about the midpoint between 50 and 52. So t-coordinate is what? 51. So equals graph 51. And what is t naught? Not 0. At time 45. And read the problem. Don't take it necessarily to be where the line starts. I may start at different places. Read what it says. So minus 45. So the delay is 6. By the way, if you had used the node equations, instead of 51, what value would I put for t-coordinate? You would have put 51 minus 45, 6. Clear, everyone? Finally, for tau, we need t63. For the slope method, standard slope method, tau is t63 minus t-coordinate. How do I find t63? Okay, let's figure out t63 now. Okay, I'll turn it over. So the whole delta y is 140 minus 150 minus 10. 63%. If you want more, I can put 63.2, but 63 is minus 6.3. So, why the measurement at T63 is going to be the original value, why not, minus 0.63 delta y. That means I have traveled 63% towards the new steady state. Sorry, plus, that was better, plus 0.63 delta y, plus. So that's 150 minus 6.3, 143.7. So T63, I read the graph, is where the measurement is 143.7. Clear, everyone? David, okay? Mika? Rim?
From where did you get 63?
Because in the standard slope method, tau is obtained by T63 minus t-coordinate.
So it's always T63.
Only if it's the standard slope method. You see, problem 2 at the exam is modification. But the standard slope method, the one you see in the Smith curriculum book, okay, uses, and that would also have been the equation. Instead of having the t-coordinate, they have the do not use time. Instead of T63, they have t do not use. For the do not use method, it would be t do not use instead of T63. So, clear now? Okay, so I need to look at the graph, and here is a mistake I see some people do. So I'm looking at time 143.7, right? Yeah. So look at where the actual data is 143.7. So here's 144, 144, 143. It's about 2/3 of the way. Looks like right about where I have it here. Careful, it's the data line, not the slope line. If you draw it at the slope line, that's a serious error. Okay? Here they're not that far apart. But again, remember, I'm grading on method. The number may be very close, but if there's a method error, you lose a lot of points. So where the blue line is 143.7. So 143.7 looks like it's about here. If we go down, that looks to me about times 68. Here I can. Yeah.
Am I gonna lose a lot of points if my tangent line is kind of sketchy?
Yes.
Really?
Not as many as you mess up the sign, okay? Nothing is as major as messing up that sign. Everything else you still get a lot of partial credit. But that sign is crucial. So let me make it thinner. So I'm looking at 143.7. Well,
You hold down shift, it'll automatically make it straight.
I know that, but I kind of want to undergo with that. Okay. Yeah, 143. I don't like this.
What? That was good.
Yeah, hold this shit.
No, it was closer to here. You can throw that.
There you go.
Yeah, that's the one. And careful, it's not where the slope line is intersected. It's where the experimental data, I'm repeating myself here, but I don't want anyone to mess it up. So
How close do you have to be? Because you're making it seem like you're really.
if it's clear that you're doing experimental data, you'll be fine. So right here is D63, if you want to do that. Right here.
My tangent line is gonna be horrible.
Yeah.
Okay? Right here is this. So that's about times 68. Okay? So from graph, by the way, if you're using the node equations, what would be T63? Okay, you give me an answer, so let me quickly.
23?
Okay, say what?
23?
Yes, exactly. You subtract T naught. You subtract the time of step change from all measured times. That's the equivalent of taking the time of step change equals 0. Okay? So we're ready now. So tau is 68 minus the corner was 51, 17. So GU is equal to K is plus 0.25. Tau we found is 17. Delay is 6. That's nice. Okay. Any questions? Good. Okay. Let's devise our own method. Remember, we can take always one point in a three-point method has to be the steady state. And how do we match exactly the steady state? How do we guarantee that we match exactly the steady state? What matches the steady state?
Picking more points.
What matches steady state then?
Infinity.
What equation, what parameter ensures, if we treat it that way, that we match exactly the steady state?
Okay.
Okay, exactly. The moment I put k equals delta y over delta u, I match the steady state. That's what is required to match the steady state. So in all three-point methods, obviously, not all points are created equal. The steady state point is a lot more significant than any other point. Okay? So definitely, we could have not matched steady state and picked any 3 points, but that would have been very bad. Okay? So 1 point is always taken, k equals delta y over delta u, which takes away 1 of our degrees of freedom, k. But the other two, tau and d, are taken by matching any 2 points. So, let's create a 3-point method. Actually, remember, it uses T75 and T25. Smith-Corripio, T63 and T28. But we can create any method we want. And so, how about if we pick T80 and T20? Okay? So let's make, okay, I need to absolutely keep this equation up there. So, okay. Two, a 3-point method that uses T80 and T20. Actually use T75, T25. Okay, let's go T80. So the first thing now is we have to get the equation. Oh, k is still the same. So 2 identical. All methods will have exactly the same k. So I need to first get the equations. So how do I get the equations? I plug in into 4 star, matching of the points. Because obviously I'm talking about having moved 20% or 8% towards the steady state and past the time delay. And past t naught plus d. So the equation that would be used is the t greater t naught plus d. Okay? So, we must have for T80 that y at T80 must be equal y naught plus k delta u, but because of this, what does it follow? That k delta u is equal to delta y. So that k delta u that you see in equation 4 star, the moment that we select k that way, becomes delta y.
Excuse me.
Yes?
Can you explain that one more time?
This is how I calculate k. Change in output, measured output, over change in input. Move it to the other side. It becomes k delta u equals delta y. So my model has k, but if I select k delta u, actually k according to this equation, k delta u is going to be equal to delta y. That's all I'm saying. And that will immediately have an important effect on that equation. And my color choice, the one I'm trying. So that is delta y. Okay? times 1 minus e to the minus t minus, oh, what is the t we have here? Should be the measured t80. At time t80, I must be at y of t80 to match the experimental. So this will be t80 now, minus t naught plus d over divided by 2. Move y naught to the left hand side. What do we have? We have y at t80 minus y naught. What's that? What is y of t80? Okay, hold on. Let me do something. What is y of t80 equal to? It's equal to y naught plus 0.8 delta y. Right? And delta y is what? Well, okay, just leave it as delta y. Plus 0.8 delta. That's how we find y at t8. Remember that calculation here, deal with 63. What's y at t63? Y naught plus 0.63 delta y. What is y at t8? Y naught plus 0.8 delta y. Yes?
How come it doesn't matter that we made those calculations with D63 and now we're using?
No, we're going to make new calculations.
Oh, okay.
This doesn't apply to this problem. Just use that to explain the concept that y at t80 is y naught plus 0.80 delta y. That's what I'm saying. Okay? So, y naught plus 0.8 delta y is y at t80 equals y naught plus delta y times the bracket. Y naught cancels out. And after you have cancelled out y naught, what else cancels out? Delta y cancels out after. So we get 0.8 equals the bracket. So follows that 0.8 equals 1 minus e to the minus t80 minus d naught plus d over down. Move the 0.8 to one side, move the exponential to the other side, and you have e to the minus the bracket over down equals 1 minus 0.8, or taking the natural log minus the bracket over down equals ln. I'm leaving it in this way to make clear what things we are going to be changing when I go to point 20. So that means that minus the bracket, and now I'll fill in the bracket, which is t80. I shouldn't have put parentheses here. Shouldn't have been a parenthesis. So t80 minus t naught plus this equals tau ln 1 minus 0.80, or that this gives me let me rewrite that as minus t80 minus t naught. I'm just putting the t naught with that, and then I have minus minus, which makes plus d equals tau ln of 1 minus 0.80